In this video, let us study the propagation of electromagnetic wave through an ionized medium. First, let us look into why we need to study the behavior of electromagnetic wave through an ionized region. We would have heard about radio wave propagation. A radio wave propagation or a sky wave propagation, which is usually referred as skip, is a type of wave propagation where the radio waves sent from the Earth's surface are either reflected or refracted back to the Earth's surface by the ionosphere region of the Earth's atmosphere. We know Earth's atmosphere comprises of many layers. About 55 kilometers from the Earth's surface, we have an Earth's atmosphere which is completely made of electrically charged ions called ionosphere, which is upper electrically charged layer of the atmosphere. This layer helps us in many ways by reflecting radio waves back to the Earth sent from the surface of the Earth. This radio wave propagation, which is a part of an electromagnetic spectrum, is highly useful in long distance communication, mobile communication, radar, and some type of satellite communication. So, it becomes an essential to study the behavior of plain electromagnetic wave through an ionized medium. There are a lot of techniques available to study the behavior of electromagnetic wave through ionized region. Here we are making use of Maxwell's equations. We know Maxwell's differential equations are written as del dot D vector is equal to 0, del dot B vector equal to 0, del cross E vector equal to minus dou B by dou T, del cross H vector equal to J vector plus dou D vector by dou T, where this D vector displacement vector is given by epsilon times E vector, electric field strength, and the J vector, the current density, is given by sigma times E vector. Sigma is the conductivity. The magnetic field strength, magnetic induction B vector is equal to mu times H vector. H vector is the field strength, and we know mu is the permeability of the medium and epsilon is the permittivity of the medium. For an ionized medium, the medium is characterized by a heavy conductivity sigma and the charge density rho is equal to 0 because no charges will be present inside that medium. The entire electric field will be concentrated on the outer surface. So, the rho will be equal to 0 and the mu will be equal to mu naught and epsilon is equal to epsilon naught. Now, let us put all these conditions, rho equal to 0, mu equal to mu naught and epsilon equal to epsilon naught in equation 1. If we substitute, our equation reduces to the first equation del dot D, in place of D we have wrote epsilon into E and rho equal to 0. So, we got del dot E equal to 0, and the second equation, the gradient of H vector, we have B, in place of B we wrote mu naught H, so del dot B H vector is equal to 0 and del cross E vector is equal to minus mu naught dou H by dou T. In place of B we have wrote mu naught H and del cross H vector is equal to sigma E vector plus epsilon naught dou E vector by dou T. So, we have named this set of equations as 2A, 2B, 2C, 2D. Then take the curl of equation 2C. So, del cross E vector is equal to minus mu naught dou by dou T del cross H vector. So, we have the value for del cross H vector in equation 2D. So, let us substitute it here. We get minus mu naught dou by dou T into sigma E vector plus epsilon naught dou E by dou T. Now, let us multiply it. So we get del cross E vector is equal to minus mu naught sigma dou E by dou T minus mu naught epsilon naught dou square E by dou T square. Let us name this equation as equation number 3. Now let us find a simple solution for del cross E vector. We have a vector identity for it. Del cross E vector is equal to gradient of del dot E vector minus del square E vector. From equation 2a, we know del dot E equal to 0. So the first term goes to 0. So del cross E vector equal to minus del square E vector. So we have named this equation as equation 4. Compare the equation number 3 and 4. We get minus del square E equal to minus mu naught sigma dou E by dou T minus mu naught epsilon naught dou square E by dou T square. Now bring everything into one side. We get del square E vector minus mu naught sigma dou E vector by dou T minus mu naught epsilon naught dou square E vector by dou T square equal to 0. So this is a wave equation in terms of E vector. This equation is obtained by taking curl of equation 2c. If in case we have taken the curl of equation 2d and do the same procedure, we may arrive at del square h vector minus mu naught sigma dou h by dou t minus mu naught epsilon naught dou square h vector by dou t square is equal to 0. So this is equation number 6. So we can see equation 5 and 6 are identical in terms of E and H, and this equation represents wave equations governing electromagnetic fields E vector and H vector in an ionized medium. And these equations are vector equations which have identical form, and each of the 6 components, that is Ex, Ey, Ez, Hx, Hy, Hz, separately satisfies a scalar equation of the form del square psi minus mu naught sigma dou psi by dou t minus mu naught epsilon naught dou square psi by dou t square is equal to 0. And here the psi is a scalar quantity and it stands for any of the 6 components of E and H, that is Ex, Ey, Ez, Hx, Hy and Hz. So we can see equation 5, 6 and 7 are of an identical form, and we can write a plane wave solution, or we can assume a plane wave solution like this. For the electric field vector E equal to E naught e power I into k vector dot r minus omega t. For the H vector it is H naught e power I k vector dot r minus omega t. For the psi, the scalar function, I have wrote it is not a vector, it is psi. Psi is equal to psi naught e power I k dot r minus omega t. This is a written error. Here the E naught, H naught and psi naught are the complex amplitudes or the constants which are constants in space and time. And here the k vector is a wave propagation vector which we have defined already. The k vector is equal to k into n cap, and this k vector is the one which represents the direction of the propagation, wave propagation, and k is nothing but it is a wave number which in turn is written by 2 pi by lambda. We know an expression for the wavelength in terms of frequency and velocity. So lambda can be written as v by we know v is equal to nu lambda. So lambda is equal to v by nu. Substituting there, we get 2 pi nu by v into n cap. And in place of 2 pi nu, that is nothing but that is the frequency of the electromagnetic wave omega. So we got the propagation vector k is equal to omega by v into n cap. And this n cap is nothing but it is a unit vector which acts along the direction of the propagation wave vector k, and here v is the phase velocity of the wave. Now, let us use the solution psi and find out del square psi from it. When you find out, you will get del square psi is equal to minus k square omega, and dou psi by dou t. If you find dou psi by dou t, you will get minus I omega into psi. And then if you do dou square psi by dou t square, you will get minus omega square psi. That is, you are differentiating the previous equation, and again you get minus omega square psi. Okay. Let us substitute this value of del square psi minus k square omega, dou psi by dou t equal to minus I omega psi, dou square psi by dou t square is equal to minus omega square in equation 10. So, sorry, all this in equation 7. So, when you substitute, you will get minus k square psi plus I omega mu naught sigma into psi plus mu naught epsilon naught omega square psi equal to 0. So, psi is common there, we can take the psi outside. So, within the brackets we have k square minus I omega mu naught sigma minus mu naught epsilon naught omega square. We all know psi is a scalar component, it has some value. So, that will not go to 0. So, the bracketed terms of the equation level will go to 0. So, what is in the bracket? K square minus I omega mu naught epsilon sigma minus mu naught epsilon naught omega square equal to 0. Keep k square one side, bring all the factors to the other side. So, bringing to the other side, we get k square is equal to I omega mu naught sigma plus mu naught epsilon naught omega square. The next step, we are taking mu naught epsilon naught omega square outside. So, when we take it outside, we get k square is equal to mu naught epsilon naught omega square into 1 plus, you will get I sigma. Since we have pulled the omega, only one omega is there and pulled the omega square outside, so we are dividing by omega, and epsilon naught is also not there, so we are dividing it by epsilon naught. So, we got I sigma by omega epsilon naught. Generally, for an ionized region, the conductivity sigma is given by minus n naught E square m into I omega. Here n naught is nothing but the number of free electrons available, the number of electrons available per unit volume. So, we are multiplying an I and dividing it by I. So, we get I n naught E square. In the denominator, you will get I square. So, it becomes minus 1. Already a minus is there. So, I n naught E square by m omega. Now, let us substitute this value of sigma in equation 12. When we substitute, we get k square mu naught epsilon naught omega square 1 plus I by omega epsilon naught. In place of sigma, that is I n naught E square divided by m omega. We all know c square is equal to 1 by mu by epsilon naught. We have seen in many of the problems, so, in place of mu naught epsilon naught, we are substituting c square. So, omega by c square into 1. I into I will give you I square. So, it is minus n naught E square divided by m omega naught c square. So, in the next step, here in the you could see n naught is a constant, E is a constant, m is a constant, epsilon is a constant. So, all these are replaced by a constant, replaced by a factor omega p, which we call it as a plasma frequency. Okay, so k square is equal to omega square by c square into 1 minus omega p square by omega square, where omega p square is equal to n naught E square by m epsilon naught, which is the plasma frequency of the medium. Okay, we all know the refractive index is defined by n is equal to c by v. So, the refractive index is equal to the velocity of light in air divided by velocity of the light in the medium, or the velocity of the electromagnetic wave in free space divided by the velocity of electromagnetic wave in the medium. So n is equal to c by mu. We have already defined k is equal to omega by v, that is the propagation vector k is equal to omega by v. So in place of v, we can write c by n. So when you substitute the phase velocity v is equal to c by n, we get n omega by c. And let us square it. When we square it, we get k square is equal to n square omega square by c square. See equation number 14 and 16 both represent k square. So on the other side also we have omega by c square. So comparing this equation, we get refractive index of the plasma as n square is equal to 1 minus omega p square by omega square. You see 14 and equation 14 and 16, compare it, you could see n square is equal to 1 minus omega p square by omega square, or n is equal to root of 1 minus omega p square by omega square. So let us name this equation as equation number 17. Okay. What if these electromagnetic waves or the high frequency electromagnetic waves are sent? So high frequency region means in this region it is the ionization is very less, not heavily ionized. So for high frequency regions, like where the frequency sent omega is much greater than the plasma frequency omega p, we could see the refractive index will be real, because omega p is very small. So omega p by omega we will get a small number. So 1 minus that small number will give us a positive value. So our n will be very real. So which suggests that the electromagnetic wave propagates freely as in the case of dielectric medium. Okay. See, if slowly the plasma frequency is increased, that means Wp is increased, what happens is omega p by omega value becomes a bigger number. So that means the refractive index in turn is decreasing. So if plasma frequency increases with the distance, the refractive index will also decrease. You could see in the first case, the plasma frequency is constant, the electromagnetic wave will travel in a straight way. In the next case, what happens in the diagram itself, you could see the dots are very less in the lower region and it is more concentrated in the higher region. That means as the wave increases, the plasma frequency of the medium is also increasing, which in turn decreases the refractive index of the medium. We know when a wave travels from a denser medium to a rarer medium, it will go away from the normal. So because of this, total internal reflection will happen. So the wave will bend and it is getting back to the surface of the earth. So when the electromagnetic wave is sent from a region of higher index to a region of lower index, the high frequency or the shorter wavelength electromagnetic waves bent by the Earth's atmosphere. This principle is used in long distance radio transmission. Okay, you can ask me, we measure distance of the moon using the high frequency wave. How is that possible? See, if ionosphere is present, these waves has to be sent back to the earth, but some waves escape the earth's ionosphere and the earth's atmosphere and reach the moon. This is because the frequency of the electromagnetic wave should be much greater than the plasma frequency. So the transmission is unaffected by the presence of ionosphere, and these radar signals reaches the moon surface and they get reflected and pass through the ionized part of, or escape the ionized part of the Earth's atmosphere. So this is the reason how electromagnetic wave or the radio waves reaching the moon. Okay, this is for a high frequency region. What if the uh, region is of low frequency, or if the region is highly densely ionized? See, if for all the low frequency region, we could see the omega is less than the frequency of the electromagnetic wave is less than the plasma frequency. So more the value of plasma frequency, we see omega p by omega value is greater than 1. So 1 minus the greater than 1, you will get a negative number, root of negative number. So which gives a complex number there. So the refractive index becomes purely imaginary. So such electromagnetic waves, when they incident on plasma, definitely will be reflected from the surface. So we can write k, that is the wave number, I n omega by c. In previous case it is n omega by c. Since it has become an imaginary term, so it is I n omega by c. So we can write I omega by c. In place of n, we can write root of omega p square by omega square minus 1. So the solution can be altered. E equal to E naught e power I k n vector into r vector minus I omega t. In place of k, we can write minus omega n by c. Already I is there and I n omega. So we got e power minus omega n by c n r e power I minus omega t. In the same way, you can write for h vector also. So which indicates the solution of these two, that is the solution in equation number 19 and 20 indicates that within the plasma, the electromagnetic fields E and H will fall off exponentially with the distance from the surface. So if the distance is more, the E and H vector are expelled away from the surface of the plasma. Now let us check for the skin depth or the penetration depth of the plasma. So del plasma is nothing but it is the skin depth, which is given by 1 divided by beta. The value of beta is omega n by c. Substituting it, we get 1 divided by omega n by c. Then substituting the value of n here, we get 1 by omega by c into root of omega p square divided by omega square minus 1. So within the square root, you cross multiply it, you will get omega p square minus omega square. So when you take that omega out of the square root, that omega by c and this omega will get cancelled. So we are left with c divided by root of omega p square minus omega square. If in case omega is much lesser than omega p, we can neglect the value of omega square. So within the square root, we have only omega p square, so which gives us del plasma is equal to c by omega p. So this is the reason why the electromagnetic fields within a plasma is expelled. So this is a well-known fact which is observed in controlled thermonuclear processes, and this has been employed in confining hot plasma within a region. So the more the density of the plasma, the electromagnetic waves are expelled away from it.